Right, we thank you for coming. This is going to be our third presentation, preliminary design review for spacecraft preliminary design. And I'll pass it on to Zoe Crane, project manager for Hera.
All right. Thank you, Dr. B. So my name is Zoe Crane. I'm the project manager for Team Asteria, and we're here today to present to you Project Hera. So first of all, thank you all so much for being here today. So to begin with our overview, essentially I'm going to go through our introduction and mission concept, our system of systems definition, our system definitions, our system validations, our system of systems validations, and conclude with our programmatics. So first I would like to introduce my assistant project manager, Madison Padilla, my subsystem lead, Michael Wigton, my other subsystem lead, Zachary Gibbons. So for our mission concept, what we're looking at is building a descent capsule that's designed as an Earth-based system that will preserve and deliver a payload from a high altitude to a designated ground station. The original idea for this project essentially is in the event of a failed launch or a plane crash, any delicate payload or information that is necessary to continue, like information in the black box of an aircraft, you can place your payload into RAPS that will then, during that aborted launch, bring itself back to a designated ground station. So we are looking at building an autonomous landing system. So moving on into our actual objectives for our project, for Hera. Hera should have a descent vehicle that soft lands to a ground station after being released from a predetermined altitude. That descent vehicle should ensure the preservation of a delicate payload during the landing cycle. And finally, a method of lifting the descent vehicle to that predetermined altitude should be created by the design team. Therefore, the requirements for Hera are as follows. Hera should have one descent vehicle called the Reliable Aerial Preservation System, or RAPS, here. The Hera system of systems shall have one lift vehicle called Apollo, here. And Hera should have one ground station called Houston, 1/4 of which is right here. This is our design structure tree. Once again, Hera is our overarching system that is made up of our 3 separate systems. And this is a render of Hera itself. As you can see, Apollo, RAPS, and Houston, where Houston actually consists of 4 columns of cinder blocks that we didn't want to carry in today. This is our general design team structure. Again, we are made up into 3 systems. So Michael Wigton is actually system lead for both Apollo and Houston, while the RAPS system is made up of Zachary Gibbons in addition to the rest of the members of our team. We also have 2 system integrators and, of course, our assistant project manager. A really fast overview of our concept of operations. To begin with, RAPS will be attached to Apollo. Second, RAPS will be raised to altitude by Apollo. We will then release RAPS and deploy our parachute. And at this point, our thruster will activate, and RAPS will soft land safely to the ground. At this point in time, I would like to pass this off to Madison Padilla to talk about our Hera definition.
All right, thank you, Zoe. As Zoe said, I'm going to be going over the Hera definition. With me today are my 2 integrators, the first being Joseph Guest, and the next being Nicholas Mallet. So part of the Hera systems of systems definition is that, as shown before, we have our Hera design tree, which consists of our system of systems and then 3 systems that will help complete our objectives. The first being Houston, which consists of the main cinder blocks that will be holding up Apollo, so that way we'll be able to launch off our ground station. The next will be the Reliable Aerial Preservation System, which will be our main descent capsule. As part of that, we will also be having the final system, which will be Apollo, which is our lift system, which shall essentially lift our RAPS, I apologize, to our altitude and release. With all of that, we will essentially go through and complete the requirements, which includes that Hera shall have one descent vehicle, one lift vehicle, and one ground station. Now I'll be passing it off to Michael Wickton to discuss the Houston system.
Thank you, Madison. I will now be going over the Houston system definition. For the Houston system, it is one of the 3 systems of the Hera system of systems. Simply put, the Houston system is 4 towers of cinder blocks. There are 12 total cinder blocks. Each tower is 3 cinder blocks high for a total height of 48 inches. The objectives and requirements of the Houston system are as follows. The Houston system should raise the Apollo system off the ground. This is so that we can place the reliable area preservation system underneath the Apollo system prior to launch. The requirements are that we have to raise the Apollo system to greater than 1 meter and less than 1.5 meters off the ground. The RAPS is approximately 3 feet tall, which is about 1 meter, so that derives our lower end of our requirements. And the maximum is to ensure that there is the minimum amount of distance between the 2 systems prior to launch. To do this, we are using 12 total cinder blocks, as I said before, 4 towers of 3 cinder blocks high. Each cinder block has the dimensions of 8 inches by 8 inches by 16 inches. The most important dimension being the 16 inches. That gives us a total height of 48 inches per tower, or about 1.22 meters. Here we mocked it up in Catia to just verify that our cinder blocks actually are 48 inches tall. And so therefore we have numerically validated the fact that we need to have the requirements between 1 and 1.5 meters with a total height of 1.22 meters for our ground station. I will now be going over the Apollo system definition. The Apollo system is the second of the 2 systems underneath Hera. This system is responsible for lifting the reliable area preservation system to altitude. As you can see behind me, we have a hexacopter configuration. Hexacopter uses 6 motors, propellers, and speed controllers to produce lift. In the middle of the hexacopter frame, we have an electronics bay which contains our electrical components, most importantly our battery and flight controller. And shown above me right here is the location of the 4 batteries, 1 in each corner to distribute the weight about the center of the system. And then in the center we have a flight controller, and just to your left is the switch that will control the burn wire system to release the RAPS. The Apollo system has an interesting set of objectives, is that it has 3 different phases for the mission of the Apollo system. The first phase is the Ascent Phase. The second phase is the hovering phase, and the final phase is the descent phase. And during the ascent phase, it has to carry the RAPS. So the requirements for the ascent phase is that we have to reach an altitude of greater than 91 meters and less than 101 meters. You may think that the 1 meter off of the clean number is interesting, and this is due to the distance between the center of gravity between the 2 systems. So the RAPS requirements are actually 90 and 100 meters. The maximum ascent velocity is 2 meters per second, and this is to ensure that when the Apollo system raises the RAPS system, that it won't swing around during flight. During the hovering phase, we have the requirements of having a maximum net velocity of 0.1 meter per second for greater than or equal to 1.5 seconds. This is to ensure that when we release RAPS, we are giving it the most optimal the best chance of dropping in an entirely vertical manner instead of falling in a direction that we do not want. And then finally, for the descent phase, we have the maximum altitude requirements of 122 meters, and then we have the maximum descent velocity of 6 meters per second. The maximum altitude is derived from the maximum altitude allowed by the FAA. The FAA actually regulates that UAVs can go no higher than 400 feet, which is just about 122 meters. And then the maximum descent velocity of 6 meters per second is to ensure that as it's falling, the pilot can maintain control, and it's actually the maximum velocity allowed by our flight controller. So now I will go into the lift subsystem of the Apollo system. This is the method of actually raising the Apollo system to altitude. To do so, we are using 6 E-Flight Power 60 470 kV variant motors, paired with 18-inch APC multi-rotor propellers. Together they will produce approximately 4.53 kilograms of thrust, which is the manufacturer rating of 10 pounds. And we have a maximum amp draw of about 54 amps. To be able to spin these propellers and motors, we're using the Castle Phoenix Edge 100 ampere electronic speed controllers. They're capable of up to 34 volts at 100 amps. As I spoke about previously, we're using at maximum 54 amps with our configuration. And to be able to power the electronic speed controller, we are using 4 Fluorion 6S 4500 milliamp hour batteries in parallel, giving us a total capacity of 18 amp hours. One thing to note is due to the nature of lithium polymer batteries, we can only safely discharge 70 to 80% of the total capacity. So therefore, we have a maximum workable capacity of 14.4 amp hours. And a 6S lithium polymer battery has a nominal voltage of 22.2 volts and a maximum voltage of 25.2 volts, which falls within the range of the Castle Phoenix Edge electronic speed controller. To control the speed controllers, we're using the NASA M-Lite flight controller with a 0.8 meter vertical accuracy on the GPS system. And for the pilot to communicate with the flight controller, we are using a Tranis QX7 paired with an XSR receiver. This operates on the 2.4 gigahertz frequency using an ACCST protocol for the communication. And then for the S-Bus protocol is the actual communication between the two with an advertised latency of 20 milliseconds. And now I will be discussing the lift structure. Over to my right, you can see the lift structure actually built with the motors and speed controllers on it. The structure itself was actually made by a previous design team from last year, and we have since modified it slightly to match what we need for our project. We have added in the electronics bay on top, located here, shown over here in white, and then underneath that we have 4 metal aluminum brackets that are going to be used to attach to the RAPS. Above me, you can see the distance between the two RAPS, attachment points. We have 4 attachment points. They're centered underneath the Apollo system. The long distance apart is 20 centimeters, and the distance into the board behind me is approximately 8 centimeters. And now we'll be discussing the burn wire subsystem. The burn wire subsystem is a pulse width modulation switch that is controlled by the receiver. This allows the pilot to be able to flip a switch on the ground that will activate the switch, which will then create a circuit through the red wires as shown behind me. To be able to test the Apollo system, we have to do a flight test. For our flight test, we're going to attach a dummy weight to the Apollo system, and then we will then raise it up to 101 meters, where we will then release the dummy weight, and then the dummy weight will then fall to the ground, where the Apollo system will then increase in altitude due to the decreased mass. We have to monitor this altitude to ensure that we do not reach the requirements or the maximum limit allowed by the FAA, and then the Apollo system will then return to the ground. From our simulations, we have a maximum ascent velocity of 2 meters per second, as shown on the bottom graph. The top graph shows a linear trail up to our altitude of 98 meters in this simulation, at which point it levels out and the velocity goes to 0 on the bottom graph, which shows that we are hovering. This happens at approximately 50 seconds after mission commencement, at which point we will then release RAPS, where the altitude and velocity both increase, the velocity more substantially than the altitude, and we reach a maximum altitude of 118 meters. This is due to the decreased mass of the flying system at that point in time. To numerically validate this, we have a total design battery capacity of 14.4 amp hours that I spoke about previously. To run the mission at full throttle for 60 seconds, we need 5.4 amp hours at 54 amps per motor. Therefore, we have a factor of safety of over 2 for the battery capacity. For thrust, we have to have a minimum thrust of 196 newtons, and this is for a 1-to-1 thrust to weight ratio, which actually wouldn't allow us to fly, so it has to be greater than that value. The 196 newtons of thrust is due to having a 20 kilogram total flying weight, 15 kilogram weight of RAPS, and a 5 kilogram weight of the Apollo system. From the motors, we have an advertised amount of thrust of approximately 270 newtons, or about 60 pounds. Therefore, we have approximately a 1.31 thrust to weight ratio, which will allow us to get to altitude. It just won't be very quick. For voltage, we have to be able to power the motors, and from their test, they use a six-cell battery test. So to be able to reach the thrust numbers that have been advertised with these motors and propellers, we have to have a voltage between 22.2 and 25.2 volts, which a 6S lithium polymer battery does for us. So therefore, this system has been numerically validated. And now I will hand it off to Zachary Gibbons to talk about the RAPS system definition.
Thank you, Michael. As he said, I will be going over the RAPS system definition. On my design team with me today is Joshua Pearson, Alan Davis, Nathaniel DePutter, and Sierra Dragon. RAPS is the third system within the Hera system of systems that I will be discussing now. RAPS has 4 subsystems: the Stabilization Subsystem, the Landing Subsystem, the Electronics and Software Subsystem, and finally, the Structure Subsystem. As you can see on the board is a render of RAPS with all the different subsystems called out. The Structure Subsystem being the frame and internal mounting components, which will help keep the system together and support the other systems physically. The Landing Subsystem is shown at the bottom, where we have tanks filled with cold gas, and a solenoid and nozzle, which will help slow the vehicle down. The Stabilization Subsystem is up near the top, which will keep us falling in a vertical manner. And finally, the Electronics and Software Subsystem, which will control the solenoids in both the landing and the stabilization subsystems. The objectives for RAPS are that it should land within a predefined radius of the Houston system. It should contain a delicate payload during the descent. It should be dropped from a predefined altitude of 90 to 100 meters. It should descend towards Houston along the nadir direction during the mission, which is straight toward the center of the Earth. And finally, it should deliver the payload safely. The requirements associated with this actually come in 4 tiers, each with varying difficulty. The primary requirements include that it should land within a circle of radius 15 meters from Houston. The payload mass included should be between 1 and 5 kilograms. And finally, it should land at a speed of less than 5 meters per second. Now, while the landing radius persists through the following tiers, the landing speed slows for the secondary requirements, going down to 1 meter per second while keeping the 1 to 5 kilogram payload. And then the payload mass increases in the tertiary and quaternary levels, going to 5 to 10 and 15 to 20 respectively, while keeping that 1 meter per second maximum speed. In order to test this properly, we will be doing 4 different flight tests, one for each of the different levels of requirements. However, they will follow the same general structure. To begin with, we will load RAPS with the payload mass that is designated for that test. It will then be attached to Apollo at the Houston subsystem as shown above me. Apollo will then lift RAPS to the predetermined altitude, and then the burn wire will be triggered, releasing RAPS from Apollo. Immediately after that release, a parachute will deploy, which will slow our terminal velocity down to between 9 and 10 meters per second, depending on our mass. The landing thruster will fire up closer to the ground, getting us to our speed requirements, and finally the RAPS will land. To talk more about these structures, I would like to call up Joshua Pearson.
Thank you, Zach. As he said, I'll now be going over the structural subsystem definitions. As you can see, it is the first subsystem under the RAPS system. And for the structure, we chose to use aluminum 6061 of a T6 timber for the framework here because of its high strength-to-weight ratio or specific strength, and due to the fact that it is inexpensive and easily acquired locally in Prescott from Prescott Steel. For the attachment of RAPS, both to the Apollo system and to its own parachute, we chose to use Vectran cord because it has a very high brake load of 1,150 newtons for a cord that's just 1.5 millimeters in diameter, and it has a very low melting temperature of just 330 degrees Celsius, which makes it very useful for a burn wire deployment system. Now we have some coarse Catia finite element analysis models. Here is a model of the L channels, specifically the vertical ones. We The highest locations of stress, as you can see, are up at the top of the beam and also will be down near the bottom. And the highest zone of displacement is through the center of the beam due to column buckling. We expect that it will experience a force of around 30 newtons upon impact with the ground for our currently predicted mission, but for the case of the model, we chose to apply a force of 250 newtons, which works off of the assumption of the highest possible impact force that would still satisfy our requirements, with a factor of safety of 1.25 included. The force was applied near the top, and we had to apply a clamped restraint to the bottom for the purposes of the finite element model. The end result being that it only displaces about 30 micrometers near the center of the beam, not enough to impact any of our structural stability or viability. And while the maximum stress is only 3.8 megapascals, the 6061 T6 aluminum has a theoretical yield stress of 240 megapascals, which gives us a very high margin of safety, as you can see. Then moving on to the feet at the bottom of RAPS, which will be along with the vertical frame experiencing the brunt of the impact force. The highest amount of force is at the top of the feet near where it connects into the frame, and down near the bottom where the bowl of the foot comes into the tube that runs up to the frame. The highest displacement, in fact, is down at the bottom around here, where it's not quite supported by the main foot leg itself, so it's just the bowl that's getting pushed up. As with the vertical frame, it's expected to only experience 30 newtons, which would then transfer into the vertical L channel. Again, we apply 250 newtons for modeling and safety purposes. End result is that it's only displacing at maximum less than a single micrometer, and it's got a very high margin of safety of over 100. For the C channel, specifically the central C channel here, which will be bearing the brunt of the main thruster force, its highest stress will be along the edges of the C channel where it is welded to the frame, and the largest displacement is along the center where the arm of the force will be acting. It's predicted by our models that our thruster will output at most 310 newtons at initial firing. We chose to apply 400 newtons in this case, which is a 1.25 factor of safety. As you can see there, it's being applied at around the center of the beam and welded near the edges. End result in this case is that it has a 14.1 micrometer displacement up near where the thruster is applied, and we have an end margin of safety of 81.5 between the force applied and it potentially yielding. For the top thruster plate where the stabilization solenoids will be attached up here, there's one solenoid on each side of it, and their forces are acting directly into the plane of the plate. For the highest levels of stress for this are right where the thrusters will be acting through, and that's also where the largest amount of displacement would be found. It's expected that these smaller solenoids output only 47 newtons per thruster. For purposes of the model, we assume 70 newtons per thruster, which is a 1.5 factor of safety in order to take into account some things that we couldn't run in this model, such as potential shear or the weight of other things. And they're in plane with the plate, as I said, and it's assuming two thrusters are active to keep us level along two different axes. And the clamps, as you can see, are where it's going to be welded to the sides of these diagonal channels. In result, we only displace half a micrometer there where the thrusters are applied, and we have an extremely high margin of safety due to the very high yield stress of aluminum of 445. In conclusion, for the structural numerical validation, the industry standard for margins of safety is about 0.25. We're far in excess of that for all of the parts that we ran our simulations on, and as such, we can consider our structure to be numerically validated. Now I'll be passing it off to Alan Davis in order to cover our stabilization subsystem definition.
Thank you, Josh. I will be going over the stabilization definition. As you can see, the stabilization is a subsystem of RAPS, and it has multiple components, it being 2 regulators here, a hose connecting it up to T-fittings, which then go to the 4 solenoids. The high pressure regulator has a maximum inlet pressure of 31 megapascals, as well as a minimum outlet pressure of 2 megapascals. The low pressure regulator has a max inlet pressure of 2.7 megapascals and a minimum outlet pressure of 862 kilopascals. This then goes into the hose, which has a maximum pressure of 2 megapascals and will be about 2.5 feet total. Then it gets in the different connection components or have a maximum pressure of 2 megapascals and will separate the air into the 4 solenoids, which have a exit pressure of 862 kilopascals with a throat area of 53.5 millimeters, which give us, and so we get a moment of 14 Newton meters. In order to validate the stabilization requirements, we need to, RAPS must land within a 15-meter radius of Houston, as well as keep us relatively vertical so that most of our landing thrusters will be used for slowing us down. So the maximum deviation from the nadir axis is 15 degrees. As you can see in our simulation, initial pitch and yaw we used was 10 degrees, which gives us that deviation to be about 14.1. You can see at the beginning, the pendulum motion is steady until the parachute is fully deployed, at which point that rate of penduluming increases, but that derivation angle is greatly decreased until the thrusters turn on, and with a deadband control, we bring us to a much lower deviation of about 4.4 degrees. The displacement is, if we assume we launch from the center of RAPS, release from the center of RAPS, when we first fall without parachute, we move only slightly. Then when the parachute is fully deployed, we move more, but the most displacement occurs when thrusters are turned on. And we end up with a deviation of about 1.4 meters. With this, we can see that both the deviation of the angle as well as displacement are well under what our maximums are, and so our subsystem is validated. Next, I would like to invite Nathaniel DePugger to talk about the landing subsystem.
Thank you, Alan. The landing subsystem consists of a parachute and a cold gas thruster. The tanks for the cold gas thruster are Ninja Paintball, super light, 90 cubic inch tanks. They have a rated pressure of 31 megapascals and a burst pressure of 100 megapascals. They weigh 1.1 kilograms each and they contain 0.015 cubic meters each. We'll be using 2 of them. The plumbing connects the tanks to the solenoid valve as well as to the nozzle and the regulators that feed the stabilization thrusters. All portions of the plumbing have a burst pressure greater than 69 megapascals and a cross-sectional area more than 3 times that of the nozzle throat to prevent flow from choking. The solenoid we're using is a high-var DO3 series solenoid with a rated flow rate just under 0.1 meter cubed per minute and a maximum operating pressure of 35 megapascals. It's a big solenoid, weighs 2 kilograms, and you can see the inlet and the outlet there. The nozzle subcomponent will be machined from 6061 T6 aluminum. It has a minimum throat area of 6.75 square millimeters, a expansion ratio of 11, and it'll be connected to the solenoid via 1/8 inch female NPT thread. The parachute we're using is a Fruity Shoots 60-inch elliptical parachute. It weighs 0.284 kilograms. It'll be deployed by a ripcord attached to Apollo, and it packs into a volume of just over 1,000 cubic centimeters. Moving on to validation, the chart you're looking at there is a plot of temperature and pressure versus compressibility. The red dot is our starting point, so when the tanks are full, we haven't fired the thruster at all. As the thruster fires, temperature and pressure decrease. As temperature and pressure decrease, the compressibility factor also decreases. What this means is that we really can't assume an ideal gas for our cold gas model. So our cold gas model assumes real gas characteristics. And here are the results from that model. Thrust starts off high, 370 newtons, and quickly drops all the way down to 25 newtons after 5 seconds of thrusting. The only portions of this chart that can actually reduce the descent rate of RAPS are when the thrust is greater than the gravity losses. You can see our gravity losses for max mass, projected mass there. Specific impulse decays quickly, and the reason that it decays quickly is because the temperature decreases quickly. Decreases more than 100 degrees Kelvin in just over 3 seconds, and ISP is proportional to temperature. Because we needed maximum thrust to weight ratio in this engine and not maximum impulse per unit mass, which is the typical design goal of cold gas thrusters, we are not using a regulator. All the regulators that may have worked were really expensive or really heavy. And so what this means is chamber pressure varies, which means that exit pressure varies, which means that ideal expansion ratio varies. So we chose an expansion ratio that was optimal for a period just before we lose the ability to reduce the descent rate of RAPS. And that expansion ratio is 11. Taking sum of forces and integrating gets us velocity or nadir speed and position. And with the maximum mass, you can see our nadir speed peaks at 1 meter per second. And with our design mass, 10.46 kilograms, the nadir speed peaks at positive 2.5 meters per second. So we'll actually shoot up into the air if we open the solenoid and leave it open. But of course, the system will pulse the solenoid, so that doesn't happen. This numerically validates our requirement to land at a rate of less than 1 meter per second. The distance graphs you see on the right, the origin of those graphs is at the point that RAPS is at when the thrusters first fire, the solenoid's open. To numerically validate the parachute, simple sum of forces equals 0. So mg equals drag, solving gets us 9 meters per second, which concurs with what the stabilization team calculated. So this validates our parachute requirement. Now I'll hand it over to Sierra Dreyer for electronics and software.
Thank you, Nate. I will be discussing the electronics and software. The electronics and software subsystem, it has a power supply, a controller, and a sensor component. This is a circuit overview of the entire subsystem, and I'll walk you through the software that was going to go on during the descent of RAPS. The IMU here is going to take acceleration data and feed it into the Arduino. The Arduino will then integrate that acceleration data to velocity and position, and using that data will determine if these solenoids need to be opened, and therefore flip these switches, open the solenoids, and as needed, and bring that back down to the power supply. Our power component is a 1500 milliamp hour LiPo battery. We will be using 2 of them. They each provide 12 volts and 1.5 amp hours. Our controller is the Arduino Uno with an advertised clock speed of 16 megahertz, 6 analog in-out ports, which we will be using to bring in the IMU data, and 14 digital I-out ports where we will be using to send information to these solenoids. Our sensor component is the LSM 303 accelerometer and magnetometer with an advertised clock speed of 100 kilohertz, 6 degrees of freedom of data collection, and is compatible with the Arduino. And this is to show the scale of how small this sensor is. And to validate the power, we have 4 stabilization solenoids up here. They each require 12 volts and a total amperage of 0.45 amps. The landing solenoid here also requires 12 volts and 2.5 amps, so we require a total power of 3 amps. Our two batteries provide 1.5 amp hours each, providing a total of 3 amp hours and 12 volts. So our system can be completely turned on for about an hour and function properly. So since our estimated flight is about 2 minutes, this more than validates our requirements for power. Our accuracy derivation to determine the precision of our controller and software is using a left Riemann sum estimation to integrate from acceleration to velocity and position. For our acceleration velocity, according to our simulations, we can accelerate from 0 to 9.5 meters per second in the first second after release. So with a 100,000 time steps per second, we are going to have 10 to the negative 4th meters per second of accuracy. And with that same velocity, with that same hertz, we are expected to drop 5 meters in the first second after RAPS releases. So that gives us 10 to the negative 5th meters of accuracy for the position sensors. And with all of this together, this proves that the electronics and software system is numerically validated. And now I'm going to pass it off to Joseph Guest to discuss the Hera system and systems validation.
Thank you, Sierra. I'll be going over the initial portion of our Hera system of systems validation. Here you can see our Hera design structure tree. It should be noted that my portion of the presentation will be going over the requirements and objectives specific to both Houston and Apollo. For the relevant Hera objectives, we have that a method of lifting the descent vehicle to a predetermined altitude should be developed by the design team. For the relevant Hera requirements, we have that the Hera system of systems shall have one lift vehicle called Apollo and one ground station called Houston. Now to briefly go over the Houston assembly, as stated previously, Houston will consist of 4 stacks of cinder blocks with 3 cinder blocks each, which will be secured together with cement epoxy and positioned under each of Apollo's legs. To numerically validate Houston, analysis was performed on a Catia model. This analysis validated that the center of geometry of Apollo was raised 1.22 meters off of the ground, which is in between the 1 meter and 1.5 meter requirement for Houston. This numerically validates the Hera requirements for Houston, that we have one ground station called Houston. To again briefly go over Apollo, the Hera requirements for Apollo notes one key point, that Apollo should actually be able to, of course, lift RAPS to a predetermined altitude. To do this, the motor assembly were analyzed. As you can see, there are a total of 6 motor assemblies spread out around the Apollo frame to provide the thrust necessary to lift RAPS. As stated previously, a required thrust of 196 newtons provides a 1-to-1 thrust-to-weight ratio. In combination with all 6 of our motors running, provides 207 newtons of thrust, which returns a positive thrust-to-weight ratio. This numerically validates this requirement for Apollo, therefore validates the Houston requirement that we have one lift vehicle called Apollo. At this point in time, I would like to hand off the presentation to Nicholas Mallet to conclude our Hera system of systems validation.
Thank you, Joseph. My name is Nick Mallet. I will be continuing the Hera system of systems validation plan right now. Specifically, I'll be talking about the RAPS system, which is the 3rd system in Hera. So looking at the relevant Hera objectives specific to RAPS, you can see that Hera must have, or should have, I should say, a descent vehicle that will soft land at a ground station after being released from a predetermined altitude. The descent vehicle shall also ensure the preservation of a delicate payload after release from that altitude, and then also throughout the rest of the landing cycle. Looking at the relevant Hera objectives, you can see that the Hera system of systems shall have one descent vehicle, and its name shall be known as the Reliable Aerial Preservation System, otherwise known as RAPS. So as you can see in this image here, There's a landing subsystem, which consists of the parachute as well as the primary cold gas thruster at the base. Those parts, or that subsystem I should say, fulfills the objective component that states that it shall soft land. Looking specifically at the stabilization thrusters, which are at the top, you can see that that part would fulfill the at the ground station component of the objectives. Looking more specifically at the structure and very exclusively at the payload bay, that would be the preservation of a delicate payload as it continues throughout the landing cycle. The electronic subsystem, which is not shown in this image, would be integral throughout the whole of the system. Revisiting each of the numerical validations for each of the subsystems, and starting with the structural subsystem, the numerical validation was shown for 4 independent elements, and additional loads were put on them higher than what would normally be expected. In these cases, we were adding factors of safety as well as worst case scenarios. In those simulations with coarse meshes, we were able to show that the margin of error was well above 0 and the industry standard of 0.25. Looking more specifically at the electronics numerical validation and looking at the amperage as well as the frequency at which we operate, we were well above the required speed as well as we met the amount of amperage that we would need for the mission to be a success. Therefore, this was also numerically validated. Finally, looking at the stabilization numerical validation, you can see that the maximum angle of the axle that goes through the RAPS system as well as the nadir direction was underneath the 15 degrees that was the maximum that we were required to not exceed. Additionally, the maximum distance from the ground station at landing through our simulation was under the 15 meters that we could exceed, or that we would have to be underneath. Finally, just to summarize the validations, each subsystem within RAPS was independently validated and culminated together and integrated. That validates the RAPS system independently. With respect to Hera, as you can see here once again, each individual subsystem points out how we would soft land a delicate payload near a ground station, or at a ground station, I should say, and at the same time preserve that delicate payload. Finally, just an overview, because we haven't talked mass entirely. The mass of the actual RAPS system without a payload but full tanks would be roughly 9.461 kilograms. And then loaded, it could go up to 3 kilograms to get to the maximum mass that we could arrest, or at least decelerate, would be either 12.3 kilograms or 12.7 kilograms, depending on the mass that we would include. And then also looking at the Apollo system, which is a part of this Hera objective, the Apollo system is capable of lifting 15 kilograms as a maximum. This is important to note because within the Hera objective, it states that we should be released from a predetermined altitude. If we're not able to obtain that altitude, then we wouldn't be able to release it. Therefore, because RAPS is underneath the 15 kilograms that Apollo is capable of lifting, we're able to release RAPS from the altitude and obtain that altitude. Finally, just one more overview of Hera. Hera consists, again, of the Houston system, which is the 4 pillars of concrete blocks, with RAPS located in the center of it, connected by cord to the Apollo system, which rests on top of Houston. Finally, to conclude the presentation, will be Zoe Crane, our product manager, talking about programmatics.
Thank you, Nick. So a brief overview of our labor hours. As of last night at 11 p.m., we had put a sum total of 1,745 and a half hours into this project. And a project budget overview. So our max budget was $1,600 this semester. So our total purchasing cost of all parts for Apollo and for Houston, thankfully we were able to snag some concrete blocks from maintenance, but all of the parts from Apollo and RAPS comes to a sum total of $970. And we were lucky enough again to be able to use a pre-existing design for Apollo itself, because as you can see from the total donated cost, Apollo right now is worth about $1,700, which is over already our budget itself. So this project would not have been successful had we not been able to use this other system. Other parts of the budget that were not factored into those numbers, we do need to pay for 3 months worth of nitrogen when we test next semester. So 3 months worth of nitrogen is about $75. And then our mock-up costs $50, going through integration, program administration, and our rainy day fund brings us to another about $400, which puts us under our budget of $1,600 for the semester, or for the year, at $1,495. But once again, we would not have been able to fulfill many of our requirements had we not been able to use the pre-existing Apollo system. So going over a brief slide, this is like 0.5% of the lessons we learned this semester. So to begin with, reading other people's code is really difficult. Please don't trust work done by other people without thoroughly checking it yourself. The problem with using another team's design is if they messed up, it messes us up. So we have had to essentially redesign and go back through the Apollo system from the beginning, which is almost a project in and of itself. So we've done quite a bit there. Updating the integration team when a design change happens is super necessary. All of the renders that you saw came into fruition approximately 3 days ago because we kept forgetting to take the skins off. This is in here for the comm professors. Please don't kill me, I did it on purpose. Capital letters don't belong in the middle of sentences. Engineers can't write. Our OCR documents took a little bit of work to go through in addition to this PowerPoint. And this final lesson is, I think, one of the most important that we've gone through this semester. Effective listening is just as important as effective communication. Communication isn't just hearing someone or speaking at someone. You have to actually sit down, respect them, and listen to what they're saying in order to get anything done throughout the semester. And I think I can say with confidence that our team dynamics are stellar. And we've been able to be very successful because of that. So kind of to wrap up, I would just like to take this moment to thank, in particular, Dr. Julio Benavides and Dr. Patrick McElwain, in addition to the remaining really great people on this slide, and also this slide. So before I open it up for questions, I would just like to say that this particular render of RAPS and Apollo is actually set over the Dells, so this is approximately what RAPS would see as it's being launched. So at this point, thank you so much for coming today, and I would like to open the floor to any questions.
Great job, guys. It's a very ambitious project. I'm excited to see how it turns out next semester. One place I want to start is slide 37. So I kind of saw this throughout the presentation. I know that you're kind of working on something that's already been designed. It seems like you had some higher level requirements and you came up with these derived requirements. I saw stuff, such as power requirements and things like that. Is that, I was trying to track on my head, is that kind of how it works? You were given the higher level mission requirements and you created these derived requirements for these subsystems?
So essentially what happens is we're given a general RFP at the beginning of the semester, and then we're meant to create our system of systems and then subsystems all the way down to different component and element levels. However, due to the very small amount of time that we have to present, we're only meant to validate our systems. The problem is you can't validate a system without validating all of its subsystems and ensuring that those happen. And so because of that, all of our different components have requirements that we did touch on, because the only way we could possibly launch Apollo and RAPS is by having enough thrust to do so and having a small enough mass to do so. So that's where those requirements came in. Does that answer your question?
Yeah, I was just trying to follow it in my head. That makes sense, and I understand time constraints. Let's see, here's another one. So slide 66. For these structural analyses, I kind of would like to see overall how this relates to the overall, because I know you said L channel, but I see some L channel on top, L channel in the middle. I'm guessing this is for the vertical pillars.
That is correct.
So from what I remember, those are the most critical components. They had a pretty high margin of safety, which is another thing I wanted to ask about. But so did you guys do any analysis on that upper structure? I know you did for the thruster plate, but that's going to impart loads on the rest of it. Did you look at that at all?
I'm going to pass that question off to Josh.
No. Not on this time. We intend to do as such by the time we get into next semester, but we would also prefer to be doing that in ANSYS, not Catia, and minor meshes, and not at this time, no.
Yeah, that's understandable, but yeah, so just because you might end up with a more critical component up there, and I was trying to picture in my head. So just as long as you guys are aware of the risks there. And I'm guessing the margins are really high because a lot of this is a lot of off-the-shelf stuff that you're kind of making work.
Essentially what it comes down to is the most accessible, budget-friendly, et cetera, metal is aluminum. So what we're looking at doing next semester is decreasing mass and thickness of the various different components, which will decrease our margins of safety because currently it's very clearly over-engineered for the loads that we're going to be experiencing.
Okay. And last thing, I really liked your lessons learned slide and the fact that you acknowledge that a lot of people see this, from what you said, this, you inherited this free, but often integrating something that already exists with a new design is a lot more difficult. The integration risks are, that's something I'm glad you acknowledge. That's always an issue.
Our integrator who worked on it is nodding. Yeah. It's a lot of hours in Catia.
Oh yeah, I believe you. So, but yeah, great job, guys.
Yeah, absolutely a huge amount of work, and much applause to you guys for working through a lot of it. A couple questions. I'm just trying to wrap my mind around a few things. And this actually piggybacks a little bit. So how did you choose which critical component, or which components you were going to analyze? Or what was your methodology for kind of deciding what the critical components were worthy of being analyzed versus why didn't you analyze the duct tape, for instance? You know, how did you come to that?
I'm going to pass that off to Josh too.
So the components we chose for this were the ones that at time of impact, thrust, and lift would be experiencing the majority of the forces. In this case, because we're moving in a more or less vertical manner, those are primarily the vertical members and the crossbeam. The reason the duct tape isn't analyzed is because we probably won't use duct tape. Maybe. Yeah, I understand they do need an analysis of them due to the just jarring force of impact to ensure that they stay connected. They
Sure.
aren't analyzed at this time due to time constraints and time constraints on our end and time constraints for the presentation.
Sure. Yeah, no worries. So I think probably my suggestion would be just walk your audience through that a little bit in terms of your methodology for how you're thinking, because there were a few places, and I think it was like slide 65-ish, where you were able to pretty quickly dive into the component level of, hey, we have each of these individual components, but some flavor of exploded view or assembly view or something. It took me a long time to figure out that the little bowl-shaped thing was the feet. And I was flipping back and forth and like, there it is, okay. So start me with the big picture and then go to the component level is my suggestion. As far as Houston, I love that you named concrete blocks. However, I think
You want it to be
might,
included.
I think you might have more than just a height requirement in terms of, you have a slide 24, your requirement slide. I think you have more than just a 1 to 1.5 meters, because I think there's a stability component. I think there's probably an orientation of the four towers to each other. I don't know if there's any kind of wind requirement, and I'm not sure if there's any kind of level ground requirement. Something tip over would be in there. So yeah, I get it, it's concrete blocks, but on the other hand, if you're gonna put it on the slide, make sure that you try and be a little thorough about it. And that was just me riffing for 45 seconds and writing down what some possible requirements are. So I'm sure that with smart folks like you, you could probably think of a bunch more.
Thank you.
Yeah, no. So probably, I think that's probably the big things is mostly just, help me with the big picture before you get to the small stuff. Most of the math looked really spot on, and all the analysis I think was really helpful. Just big then small.
If anybody wonders where the great engineers of the future are coming from, all you have to do is sit in this room for a few hours and that question gets answered. I mean, you guys, all the presentations I've seen today have been so impressive. So, now, having said that, I have to admit to how I view the plane. Because, and if this was only me and nobody else in the room didn't get this, I didn't understand the stabilization system. There was all this plumbing and all these components, but what is being manipulated, or what physical principle is being brought to bear to allow you to have this stable system? If I'm the only one who doesn't understand that, you don't want to go through a long explanation, I'll just talk to the stabilization guy after this is over. But are you manipulating mass? I don't think you're not using you're not using thrusters except to land the thing. So I don't think that's part of it. But it wasn't clear to me from the presentation what was the principle of stabilization that all of that design was to implement.
So to begin with, starting big picture, we actually do have, there are thrusters up here. There's one thruster on each side of this mounting
Maybe
plate.
you said that and I just missed it.
Either way, this is a lot of information.
Okay.
It's completely fine. So there are 4 thrusters up here on each side, and so our cold gas thrusters are not just the landing singular thruster. Our cold gas also gets fed up into our stabilization.
Okay, so those sources are feeding both the attitude stabilization system and the landing system.
Correct.
Okay.
Yes, and then if you, whether or not that answers your question, I can give it back to Alan for more detail. But that's going big picture and then small pictures. It's thrusters.
Either I missed it during the presentation, but I think your comment about starting with the big picture and then working down to the details is a good addresses that. But I mean, that was just an aside. So.
I can pass that off to Alan if you would like me to.
No, I think I got it. And then my final comment is also about your lessons learned. I think your last lesson should be in large capital letters, all caps.
Probably.
And I mean, I couldn't think of any number of situations in our world today where listening is just as important, if not more so, than speaking about it. So that's deeply appreciated.
Thank you very much.
Just echoing the sentiment, definitely nice work.
Thank you.
I really only have one question and then just a couple of comments. Slide 60, you're discussing the change of requirements, primary, secondary, tertiary, quaternary. I think I missed as to why the mass requirement keeps changing.
So our requirements for RAPS and Houston and Apollo come directly from our assigned RFP. So our mission, in order to achieve mission success, we must fulfill our primary requirements, and then the remainder of our RFP are the secondary, tertiary, and quaternary.
But the only thing changing is the actual mass of RAPS, so why is the mass changing?
That is what was given to us in the RFP. That's our actual mission, is not only should we be able to design these systems, we should also be able to design them to be able to deal with a variable mass.
Okay.
So that's why the mass changes, because of course the thrust algorithm that you use and the thrust numbers you use for a 1 kilogram mass are entirely different from what you'll use for a 15 kilogram mass. And so that's why we have differentiating levels of requirements. Does that answer your question?
It does, it's just strange is all, but
Yes.
makes sense, okay. First comment is just more on formatting. The breakdown is good, I just think you should have put the overall system of systems towards the front and then broken down into the systems and then subsystems after that. It just kind of flows a little better.
Sorry, can you expand on that a little bit, because I'm a little bit confused.
So you start off with the individual systems, so you have, okay, here's a quick Hera overview, but then you're going into Houston, and then RAPS, and, Apollo. But then towards the end, it goes into a much more in-depth system of systems assessment, starting, what's this? Around slide 111. I just think that information would have probably flowed a little better if it was near the beginning, was all.
Okay, thank you.
Yeah, there's nothing major, just kind of nitpicky. And then the only other comment I have is, I would emphasize looking into the design of the nozzles for the thrusters, because the project that you inherited here, they had issues with choked flow that they weren't anticipating due to unforeseen circumstances. And just for sake of project success, it's just one of those areas I would recommend looking into.
Thank you.
Absolutely. Nice job.
Thank you again.
Okay, excellent job. On slide 88, you show that in the simulation, the distance is about 1.4 meter. Now, if you go back to 59, is there any chance you are going to land on Houston? Are you planning to remove Houston after takeoff?
Yes, and I'm going to pass that to Zach to kind of expand on that.
So currently what we're looking at doing is potentially putting Houston on like a cart. There's going to be a 50-meter safe radius that we're not allowed to get into, so we can't physically go in and pick up Houston and move it. However, what we're looking at doing is removing it in some other manner, potentially using a cart with a long rope to pull Houston, outside of the 15-meter landing zone. That way, if we do end up fulfilling the requirement, we will not land on Houston and potentially damage RAPS.
Or you can just like tip it over.
Does that answer your question?
Absolutely, yes.
I think so.
So, yeah, on the finite element analysis, 69, 66, 69, and so on, you present first the analysis and then you explain how you apply the loads. I would do actually the opposite. I would explain first where the load, like 70 first, because 70, you go 70. Yeah, here you explain where the loads are coming from, and then you show what is the results. And then if you go on 72, I would definitely expect to see the maximum stress in the middle of the beam on the top surface. I do think those are stress concentrations. So, and due to the fact that you really use a very, very coarse mesh. So yeah, you do a mesh convergence studies on all these components, or start with very refined mesh. And you can see that very well on the plate, which is I think after this one. Yeah, so go one more. So the small tetrahedron in the middle, the yellow one, gives you an idea of what is the mesh size. And then you see the thickness of your plate. So you have a mesh element that is much larger than the thickness. You should have at least 2 elements per thickness. But I mean, these are all very engineered, so I'm not going to fail. Just a side comment when you do final element analysis.
Thank you.
My Catia students. Now, 95. Who is going to machine the nozzle?
Nate.
I talked to Ernie Stokesbury about machining it, and he said he could do it before he gets the CNC lathe, but he would like to do it after he gets the CNC lathe, and he's supposed to get it over the break, so timing pretty good.
Okay, so you have already the profile well defined, I see all the areas and so on, so you spoke already with him how to
Yes,
do
yep.
Excellent. And you have also nozzles for the small thrusters, for the stabilization thrusters?
I'll pass that to Alan for that question.
Currently, we are not using any nozzles because the flow rate and throw area already gives us a force that's well over what we need. So that way we don't produce even more.
Now, on 104, what is the frequency of your control loop? So how many times per second are you checking the data from the IMU and sending control signal to the 4 solenoids?
I think I remember the number, but
our solenoids react at about 10 hertz total in comparison to the much higher software computer speeds. So we'll be, as we work through the actual code next semester, we'll be figuring out how to finesse that.
Mm-hmm. So your total descent is going to be how many seconds? Like 4 seconds? It's after you deploy the parachute. I mean, after you start actually activating the big nozzle on the bottom. So the last phase of your descent, how long is going to last?
I'm going to pass that to Alan, who headed up our simulations.
So if you were to pulse the system, which is what we're doing, it's going to last about 2.5 seconds to 3 seconds, depending on what altitude you start that thrusters. If you do how Nate was explaining during the presentation and just full thrust, it'll last about 2 seconds.
Okay, so it means then if you control the thruster at 10 hertz, you have at most like 30 control actions that you can do. And so you have to use those 30s to really make the descent vehicle stable. Okay. It may be a little bit on the, you know, on the limit, but it works. So 108, actually 107 first. Perhaps use a high, since you have some budget left, I would perhaps say use a little bit higher end IMU, because IMU is going to be really critical. I know you did that calculation about the precision, but you don't take into account the noise to signal ratio there. There might be a lot of noise coming from that. So theoretically, yes, that is a precision, but in real life, it's going to be way lower because of the noise to signal ratio. Yeah, so that was a side comment. And then 108, 110, you see, I'm very picky, but amps measure current, and so you say power needed 3 amps. Power needed 3 amps, like current needed 3 amps or power needed 3 watts.
It's been a long time since I've taken Introduction to Electrical
Yeah,
Engineering.
but yeah, this is a review, you know. Okay, finally 138. Are you planning to have a camera on Apollo to film and have drones flying around to film something very cool?
So as far as I'm aware, currently we don't have a camera on RAPS itself or on Apollo. However, we do have different UAS kids who are wanting to fly their drones around as we launch. So we should get some really rad footage for next semester of this, either going wildly well or really badly. Obviously it's going to go well. So yes, we will have some footage of the process.
Excellent job.
Thank you so much.